Hi, it's time for another math easy solution. Time to discuss further into approximate integration and now look at the method that's called the Simpson's rule. This was basically named after Thomas Simpson, and I'll explain that further down this video. Basically, in my earlier videos, I went over integration approximation methods, including the left endpoint, right endpoint, trapezoidal, and the midpoint rule methods. Yeah, but another rule for approximating integration results from using parabolas instead of straight line segments to approximate a curve. Straight line segments such as trapezoids or rectangles, etc. So if we use parabolas, the resulting approximation is called the Simpson's rule. And basically, as before, we divide the integral we are approximating at this interval a to b into n subintervals of equal length h equals delta x, which equals b minus a over n. So this is pretty much the same method of deriving all of these other rules in my earlier videos. But this time we assume that n is even, and the reason for that is because in this derivation we're going to look at consecutive pairs of intervals, and then we approximate. So on each consecutive pair we approximate the curve, but for this case fx greater than or equal to 0. But I'll explain later that even in this derivation we're looking at where fx greater than 0, but it still matches or works for any value of f of x as long as it's continuous by a parabola. So we look at consecutive pairs of intervals, and then we approximate by using a parabola, and this will make more sense as I illustrate it below. And then if yi equals to f of xi, then the parabola here pi of xi yi, in this case I'm writing it as two variables. This will make more sense later down the road as well. And this is just a point on the curve lying above xi, and a typical parabola passes through three consecutive points, pi plus 1, and pi plus 2. So this looks a bit confusing, but if you start drawing it out, it makes a bit more sense. So if we draw an y axis like this, draw a random curve like this. So now at this point, this is our x, this is our a, this is equal to our x0. And then at the farthest point here, this is our b point, this equals to xn. Now in this function here, that's our f of x right here. And now let's, for illustrative purposes, let's break this up into 6 intervals or subintervals. So this equals to, let's go to x6 for our example. Actually, I'll write this in red just to show that we're just making a general case here. So now if we break this up into let's break this up into half. So we need 6 subintervals. Again, it has to be even for this derivation. So we have here, this is our x5, this is our x4, our x3, and then break this up into 3 like this. There is our x1, our x2. So first of all, we know that the distance across, I'll change the color, so distance across here, this is our delta x, and again we let it equal to h, so h equals delta x, and this is just the total distance, which is b minus a. So that's over here. This is b minus a is a total distance. To get all of these exact same distance, this is all delta x. This is just b minus a over n. Okay, so now getting back to our parabola estimation. So at these points, this point, these are all on the parabola we're going to estimate, and it's on the curve. For example, here, this is f of x5. This equals to, well, we'll call this y5 is the distance. And yeah, so at this point, that's our f of x5 equals to y5, and also this equals to our p5, and then we have x5, y5. So this is just notation what we're writing it at. So at this point here, this is our p6, this is our p4, p3, etc., p2, p1, and this is our p0. And then now when we estimate it, so again, this starts making more sense now, why this yi equals f of xi, etc., pi, xi, yi. So in this case, f of x is greater than or equal to 0. but it turns out it works for any value, even if it's less. So what we have now is a typical parabola passes through 3 consecutive points, pi plus 1, and pi plus 2. And as well here, that's pretty much the same thing as this point here. On each consecutive pair of intervals, we approximate by a parabola. So here's a pair, so this is a pair, here's a pair, here's a pair. So that's why we need even number of intervals n. So now we approximate by parabola. Just draw a random parabola like this up to here. So it goes through the 3 points. Now here's one like this, and then this one, just to get a rough estimate, something like that. And this red right here is our p curve, which is our parabola px and y. Now to simplify our calculations and pretty much in getting an approximation for these parabolas, let's just consider the case where x0 equals negative h and x1 equals 0 and x2 equals h. So this is going to be pretty interesting derivation to get to our final approximation. So if we write something like this, just so it becomes easier, we have x0 is negative h, so that's x0 equals negative h. x1 is 0, so that's x1 equals 0. And now we have at this point cross x2 equals to h. So they're all separated by h. So we have a pair of intervals right here. These are 2 right here. So now, and we know that the points on the curve, let's just say the points on the curve are here, and so let's put it down here. This one we'll call this P2, which is h, and then y2. And again, y2 is just this height, y2. And that's the third point on this parabola. And this one is P1, which is a second. Let's just say this is on it. This is P1, and this is 0, y1. And then let's say this point here is over here, which is on the function we're trying to approximate and the parabola. So that's just putting it down right here, just to make it easier to draw for me. So P0, this is negative h, y0. So now we're going to just draw a parabola that connects these 3 lines. So this is how the parabola looks like. So what we want to do is find the area underneath this parabola. And again, this is our p, pxy. And the actual function, it could be something else, or how it looks like. For example, the function could be anything like, let's say, like this. It could be something like that. That could be the actual function f of x. So we're looking at just these 2 intervals. So now actually, before I get to that, this f of x, again, that's just our y. Now and before finding this area right here, the parabola, what we're gonna do is first need to find out the equation of a parabola. Well, we know from our earlier videos that the equation of a parabola is written in the form y equals ax squared plus bx plus c, where a, b, and c are constants. Thus the area under the parabola from x equals negative h to x equals h, well, that's basically just the integral of this. So we have negative h to h of ax squared plus bx plus c dx. So that's this, this is a parabola right here, the red. We're trying to approximate it. That's using this. And now what we could do is simplify this by using the fact that the fact for even and odd functions. What I mean by that is if we break this up into negative h to h of ax squared plus c, because these right here don't change if you have a negative value versus a positive. So negative h put in here, it's just going to be squared. And then if you put an h in here, it's going to be the same as putting a negative h inside. So I'll go dx right here, and I'll explain this in a bit. Negative h to h of the bx. So we take this out of there. So it's the same thing, we're just breaking this separately. Now this right here, this is an even function like I explained earlier. You can see also in my video on even and odd functions. If you look at how this looks something like this, where this is positive, this is always positive right here underneath the curve. This is y, this is our x. So it looks something like this. So that means, so if we're going from, let's say, negative h to h, it's the same thing as going from 0 to h twice. So this part right here equals 2 0 to h, or 2 times 0 to h ax squared plus c dx. Because again, this is positive, and it's going to be the same negative or positive side of the x value. So now if we look at this one right here, this is an odd function. And the reason here is this x value. If you put an h, it becomes bh. If you put a negative h, it becomes negative bh. So the graph looks something like this. Y, this is x. So we have a plus, and then we have a minus right here. So if you're taking an area which is going to be the net difference, negative h to h, these cancel out. So this right here goes to 0. So this is all we're left with. So we're left with this right here, which is our area, simply equals to this. And now we could solve this. So solving this equals 2, just integrate it. We have ax cubed divided by 3 plus cx, now from 0 to h. Plug that in, we have 2, plug in the h, we have right here h cubed divided by 3 plus ch. Now if you plug in the 0, well, we just get 0 everywhere, so we can ignore that. So we have this, and now what I'm going to do is multiply this inside, and I'll show you why. So 2 over 3 h cubed plus 2ch. Now what I'm going to do, this is because later down I'm going to replace part of this equation, and you'll see why I'm doing this in a bit. So I'm going to multiply by 3 over 3 here, so we're not changing anything. And then I'm going to take out h over 3 from both sides. So we get h over 3 times it by 2 times now squared, plus, well, we took out a 3 and an h, so we get, there's a 2 and a 3, so 6c. And you'll see why we're doing this soon enough as I get down further into proof, and why we're basically going to replace this a and c, so we're not dependent on these constants. Yeah, and that part right here, well, we know that since the parabola passes through the points p0 of negative h, y0, and p1, 0, y1, and p2, h, y2, and that's exactly what these points right here, these are the 3 points, so passes through those. So what we have is, well, first of all, we know that the parabola p, this is written as y equals ax squared plus bx plus c, and you can learn more about parabolas in my video link below, why it's written in this form. So we have this, that's our parabola. Now the first point p0, that's going to be y0 equals 2. Now we have a, and then put a negative h, that's our x. So we have negative h squared plus b times negative h, so we just put a negative here. So negative h plus c. And then this right here, this negative h squared, that's the same thing as, well, h squared, like I explained before in this even part right here. Because it's squared. Negative times negative is positive, so it's the same thing as writing h squared. So now p1, what we have now is y1 equals 2, well, x is 0. So 0 plus 0 plus c, that's it. And then p2, this is our y2, this equals 2, well, x is h, so we just plug in h inside. So we get ah squared plus b times h plus c. Now notice this, if we add up y0 with y1, we get 2ah squared, then these cancel, plus 2c. That's almost identical to this 2ah squared plus 6c. So that's, but we have a 2c, so we just times this y1 by 4. So what this means is y0 plus 4y1 plus y2 equals 2, well, 2 AH squared. And then we have, well, 4y, which is 4c, and then these BH, and then plus this negative BH and plus BH cancel, so we're just left with 6c, because there's a c, that's 2 c's, plus 4c. So we get this right here. And now what this means is we can replace this, so we're not dealing with the constants anymore. Yeah, and thus the area under the graph can be, under the parabola can be rewritten as, and I'll write that in a bit, basically first noting that we are not dealing with the constants a, b, and c anymore, but rather just the y values. So we got area equals 2, we'll scroll up, we have, well, h over 3 times it by, now this part, y0 plus 4y1 plus y2. So now we just need to solve for, well, we just need to know what y0, y1, y2 are, and we can do that because we know what our f of x curve is. And now we again don't need to know a, b, and c. And this means that now if we shift this parabola horizontally, we do not change the area under it. Yes, since the equation for there is dependent on the y value. So what I mean is, if we were taking this parabola, anywhere we move it now, the only thing that's changing is the x values, but again, it's not, our formulation for area is just dependent on the y value. So we can move this across to the right, doesn't matter, it will still be the same area. And this means that we can extend this for any two pairs of intervals, for example, the area under the parabola P2, P3, and P4 from x equals 2 to x4. That's just going to be, well, area in this case equals 2. It's going to still be h over 3, and now we just have y2 plus 4y3 plus plus y4. So exactly the same thing here. And that's our new area. And now if we extend the areas under all the parabolas in the same manner and add the results, what we get now is the integral from a to b of f of x dx. Yeah, it's going to be roughly equal to every single one of these areas. So h over 3, and then we have y0 plus 4y1 plus y2 plus h over 3. And now we have a y2, so we start off on the right side of it. So y2 plus 4y3 plus y4, and then plus etc. We keep going on and on to the last one, h over 3. Then we have y of n minus 2 for yn minus 1, and then we get yn. And seeing this visually here, going back up to here, so again we go from 0, 1, 2, and then we go to this one, 2, 3, 4, and then 4, 5, 6. So these always get repeated twice. So this gets repeated inside both of these parabolas that we're using to estimate. And now if we simplify this further, this equals 2, taking out the h over 3's. So take it out, and now what we're dealing with is, now we just add up everything. So we have a y0 plus 4y1, and now the y2 occurs twice, so we have plus 2y2. And then we have, well, plus 4y3, etc. And again, what we get is now this y4 occurs twice, because the next one's going to have a y4, so that's going to be 2y4, and then we're going to keep going on and on. Well, I'll just write plus, now we have a 4y5, erase this, y5 plus, etc., all the way until we get this part right here, which is 2yn, because there has to be another one before it, yn minus 2 plus 4yn minus 1, and then the last one is just simply yn. And now, important to note the pattern, we have 1, 4, 2, 4, 2, keeps going on, 4, 2, 4, 1. So we have 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, and then we just have a final 1 right here. So it's just 1 followed by a bunch of 4, 2, 4, 2, etc. and then we end off with a 1 after the 2, 4, 1. So it's always 4 at the second, 4 last, and 1 at the last. Last and first right there, like that. And now one final note before we get to the history of the Simpson's rule. Basically, although we derive this approximation for the case which f of x is greater than or equal to 0, it is actually a reasonable approximation for any continuous function. So now it is also called the Simpson's rule after the English mathematician Thomas Simpson, and he lived from 1710 to 1761. He worked as a weaver who taught himself mathematics and went on to become one of the best English mathematicians of the 18th century. And another part of this little history lesson, what we know as a Simpson's rule was actually known to Cavalieri and Gregory and other, I believe, English mathematicians in the 17th century, but Simpson popularized it in his best-selling calculus textbook, A New Treatise of Fluxions. And interestingly enough, fluxions is the original term for derivatives, which was introduced by Isaac Newton in 1665 and generally denoted with a raised dot. So for example, y dot or f dot. So these are the derivatives. Let's write this using the f one. So if we have this, that's the derivative, or the second derivative right here, versus what we know as derivatives as d of f of x, and the second derivative we get, well, d squared f over dx squared. And Leibnitz, I think that's how you pronounce it, yeah, so another mathematician, he used a derivative notation, and he denoted them by df dx or d squared f dx squared, exactly as I've written above here, etc. And he eventually won the notation battle against the dottage, named after, well, or called after these dots above the f right there, of Newton's fluxion notation. So that's just pretty interesting history lesson for you. And now to recap on the Simpson's rule and using f of x instead of y, we have Simpson's rule from integral from a to b of f of x dx is roughly equal to Sn for Simpson, delta x over 3, delta x is our h, and again this is our h that we used, and f of x 0 plus 4 f of x 1 plus 2 f of x 2 plus 4, and then plus 2 plus 4 all the way till f of x, and at the end where n is even, and where delta x equals b minus a over n, which is the interval distance, or the width of each interval, and it's equals h. And these ones here were all written as, well, we know that y I equals to f of x I. So this is just for reference, is what we used in our derivation to make it easier in writing, but they're all the same thing. Anyways, that's all for today. Hopefully you learned from this pretty interesting video on approximate integration using Simpson's rule, and also the history lesson on Simpson's rule and Thomas Simpson and fluxions versus derivatives. Anyways, that's all for today. Hopefully you learned, and like always, you can download these exact notes in the link below, and stay tuned for another Math Easy solution.